Hey there, my name is Alejandro, and welcome back for day 72 of me doing the NeetCode 150 challenge. So today we're doing another LeetCode medium backtracking problem, and without further ado, let's get straight into it. Okay, today we get LeetCode medium problem 40, combination sum 2. Given a collection of candidate numbers candidates and a target number target, find all unique combinations in candidates where the candidate numbers sum to target. Each number in candidates may only be used once in the combination. I see. Note the solution set must not contain duplicate combinations. Okay, this actually, in my opinion, this actually makes the problem easier than combination sum 2. Oh, and it seems like I've solved this before. Holy crap, when did I solve this? Submissions, August 12th, 2024. Oh, what? Was this one of the daily LeetCode challenges, or was it something I did on my own? I'll have to check, but this might have been a daily LeetCode challenge. Right, okay, I have a self.memo, so I probably did some DP stuff. Okay, although I should probably erase this, whatever this is. I did not see too much stuff. I saw backtracking stuff. I didn't see DP stuff. Oh, there's literally a 2 in the name. Okay. So, sorry about that. I'll have to check, what problem I solved on August 12, 2024. But that might actually be one of the daily LeetCode challenge problems, so we'll see. But now we'll do it now that I'm a little bit beefier with algorithms, so we'll see. But yeah, okay, so this is quite simple. Yeah, the very first thing that came to my mind was DP, not backtracking, but I guess it is. Yeah, you're not trying to minimize or maximize something, right? Because the point is that you're returning an output of the things, right? So that's why it's backtracking, not DP. And we can essentially use the very same trick as the last video for essentially not having duplicate solutions, right? Sort a permutation and essentially add that to a set and then return it as a list, right? And here's we barely have enough elements anyway that we can actually afford to do something like that. So for now, let's just do a function called backtrack. Here we'll take in a self, we'll take in an index I probably. Here we'll do, self.candidates is equal to candidates, self.target is equal to target, return self.backtrack. Here we'll do an index I is 0, probably an empty list, right? So we'll do an int, we'll do res is equal to a list, as always. Here we'll return none, so here we'll have a self.res is equal to this. We'll do self.backtrack, and then return self.res, right? And so to do will be make this a set to get rid of duplicate combination. There we go. Okay. Okay, we'll worry about that last. Whoops, my sandal. Okay, backtrack. All right, let's give this bad boy a shot, shall we? So if I is greater or equal to length of self.candidates, here we'll return, here we'll do, here what shall we do? We'll do, self.res.append a copy of res. And here we'll return. Otherwise, it's like case 1 will be include num at index I. Can only do this once. Right? So that's why I say, in my opinion, this actually makes the problem easier, right? So, because here we don't even have to call backtrack on the same index, right? We can just move on forward. So I guess it doesn't make it that much different, right? Instead of I plus 1, you just do I, or instead of I, you just do I plus 1. So yeah, you just gotta know what to do. So here we'll do backtrack, but this time we'll increment the index no matter what, right? And here we'll do res, but of course we need to do res.append self.candidates at index I. And then here we gotta do res.pop. Res.pop, case 2, don't include num at index I. Right, so before before we only did I, right, because it's you can repeat yourself and so on. But if you don't want to do that, and that way we have a termination case. If we have a termination case, also we should do if we should probably have a current sum variable, right? But here we'll do a cur sum. 0, 0, and here we'll do current sum as an int, right? And here we'll do at any point if cur sum is greater than self.target, right? Are all the numbers positive? They are indeed. They are indeed. This makes life so easy. We'll do return because we don't want to consider any more solutions. It is impossible to reach target. Otherwise, if we get to this point where we have like, considered, every number, not necessarily included it, but we reached a case, here we can do actually, here we can do if cur sum self.target. Here we'll get rid of this and return. There we go. So these are the load modifications we need to make. Right. Otherwise, if cur sum is greater than target or I is greater or equal to length of candidates, we return. That's fine. We'll just keep it in there for now. No more possible solutions. There's a pop. Otherwise, self.backtrack from I+1 and res, and there we go, right? Run something like this. We might need to include the duplicate cases. A comma, eh? What comma? Right there, I forgot a comma, Self.target. I+1, cur sum. So candidate is equal to self.candidates of I. We will do candidate res we could also check if it exceeds, but whatever, we'll just check it when we get to that call and so on. A tiny bit more inefficient, but in terms of asymptotic complexity it is the absolute same. So here we have backtrack I+1 cur sum plus candidate. Otherwise, if we don't include anything, we don't touch the res, we don't touch the current sum, and there we go. Okay. So yeah, so here, yeah, it's mad that I have duplicate solutions. So that's why we're gonna change this to a set over here. Bada bing, bada boom. Here we're gonna do res.add a tuple of sorted res and here this might not work, but we might just be able to just return as a list. Yep. So here we'll return this as a list. And there we go. Works like an absolute charm. Bada bing, bada boom. Let's give it a shot. Is it too slow? What's going on over here? What's going on, my dudes? All right, TLE. Okay. Oh, I see. We might need a little bit of caching up in this business. So, okay. Usually, because it was a NeetCode 150 problem, I was like, okay, backtracking means that, like, hey, we can just brute force our way through this thing. But okay, we can do a little bit of intelligence time over here. Oh, is this the one that I solved with Gabriel? Where Nor gave us that cool trick or whatever. Oh my goodness. Oh, what was that cool trick? Oh, yes. I remember this. Nord called me that day and told me something genius, but I forgot what that genius thing was. If I'm thinking of the correct problem, but I remember looking at something like this and having that exact reaction. Instructive moment, instructive moment. So this is a time to prove myself to see if I've actually learned anything. Okay. Okay, so this is the moment, this is the time to be clever, right? It's like, a band solution kind of thing. One thing I can do is just do a self-taught memo. Let's go to this. We can even make this a set. A memo of, what should we do? For now, let's do tuple res, tuple sum, tuple of res, tuple of cur sum. Although this is going to be oven for no reason. Okay, something like this might not be enough though. Oh, it is indeed enough. Okay, so technically we've solved it. There we go. Bada bing, bada boom. So yeah, a little bit of caching goes a long way. That's actually crazy, right? Because res, usually I was doing O of 1 operations with it. Now I'm doing O of n by converting it to a tuple. But it makes it fast enough such that we don't TLE. But yeah, that way it's like, if we see a bunch of ones, then it's like, you want to see them again, I'm like, stop right there, homie. All right? You're not doing more. All right? All right? All right? No mas. No mas. So that makes sense. That makes sense. That makes a lot of sense. It just makes me curious. What was the genius solution? Since we've covered this solution before. Also, tuple res will always have the same sum, right? So here we can just do tuple res. Ba-da ba-da ba-bow, ba-da ba-da ba-bow, ba-da-da-da-doo, doo-doo-doo-doo-doo, ba-da ba-ba-bow, ba-da ba-da ba-bow. Ba-da ba-da ba-bow, ba-da-da-da-doo. Yeah, 79 MS, but we're still much slower than the rest of the crowd. Since we've covered the solution before, remember this so as to do it again next time. For next time. Okay, so this is one way to do it. Obviously, we're terribly slow. So that's the only not cash money part about this. Yeah, so we'll do this. We'll submit one more time with my new comment, just so that that's generated nice and cool. So yeah, 69 MS, but we're still far from the crowd here. So what genius idea do people have? Each number in candidates may only be used once in combination. Yeah, each number in candidates can only be used once, right? What was the genius thing Nor did where it's like, okay, if you've used the number before, yeah. I remember doing something with like band nums or something like that. I forgot what it was that I did. I generally forgot what it was that I did. Yeah, I kind of forgot. It was some type of band num idea, right? Let's see if I can try to recall this. Given a collection of candidate numbers, a target number target, find all unique combination of candidates where candidate numbers sum to targets. Can I even do I? Is this a secret? No. Of course not. Of course not. What am I saying? Candidate numbers, candidates, and a target number target. Find all unique combinations in candidates. Right, so obviously, if we remove this, we're gonna TLE, right? So let's remove this and go back to TLE time. So yeah, so this is the case where we TLE, right? So the fact that we have a bunch of ones is quite annoying, Obviously, like, yeah, this is just gonna make me slow for no reason. Yeah, so 1, 1, 1, 1, 1. I do the case with it, case without, right? Actually, no, that's exactly what I'm... Yeah. So... Wait, no. Yeah, if the numbers are the same... Yeah, no, that's essentially what I did last time, right? Where it's like, you know, if I revisit a number again, then it's like, okay, I've had this number this many times. Right, where essentially like I have frequency mappings. But then why is my solution so slow? The idea essentially is if you pick one again, right? And then you go into the case where you don't pick it, and then you pick it again, it's like you're diverting in two branches where you're essentially doing the same work, right? Is it one of those where it's like, you know, if the number you're looking at is the same as the previous number, that's like, be like, nah, bro. Right, if it's the same number each time, you don't want to branch into each specific one, right? You want to do one where you have one. You want to have one where you have 1, 1. You don't want to do this one and then this one as your next 1, 1, and so on. So until you reach another number, You don't want to do that case. We'll do prev num is equal to none. And here we'll do candidate prev num. Prev num right, where it's like I want to do the include case. Something like this? No. That worked, but does that always work? You know what I mean? It does always work. Interesting, interesting. So yeah, I'm on the right track in terms of ideas here. Yeah, I'm definitely on the right track here. Yeah. So yeah, what does that work in a case like that? I want the case where I'm doing bad again. So yeah, let's remove this work so that I now fail again. Let's TLE, let's analysis time. It's analysis time, analysis time. So yeah, so when you have a bunch of ones, right? So the point is that like essentially you're gonna branch out. So I have two cases, right? Backtracking where I do it and not, right? So at the very beginning I'll add one, right? And then it's like if I backtrack normally, right? I have the case where I have just one. And this will grow into the cases where I have, you know, 1 and 1 as well as 1. Right? And these will grow into the cases where this is 1 and 1 and 1 with 1 and 1 as well as 1 and then 1 and 1, right? And so obviously this is repeated work, right? And then these will come into, this guy will be 1 and 1 and 1 and 1 as well as 1 and 1 and 1. And then this guy will become 1 and 1 and 1 as well as 1 and 1. This will become 1 and 1 as well as 1 as well as 1 and 1 and 1 as well as 1, 1, right? So obviously, like this and this is a bunch of repeated work, repeated. And so it's just like an annoyingly large amount of repeated work, right? But if I always do it where no, I can't do it here, right? Because if prev num doesn't equal candidate, then I'll miss some cases, right? Yeah. But here it's completely fine because this will add the cases that I need. It'll get greedy and add the cases that I need until I get to the point where I don't, and then from then on it's like I start merging, right? Because okay, that's actually super clever. It's just, yeah, I don't think I would have like ever figured that out on my own if it wasn't for that call from Noor literally on August 12th or whatever, whenever I did this problem and so on. Yeah, I'm glad I remember that. That means with the LeetCode I'm learning the cool stuff and so on. But yeah, I kind of had to remember that cool trick. I mean, we still would have solved the problem, right? Because we would have done like, you know, this trick over here. But yeah, can I do tuple now of res or no? No. I've got duplicate solutions. Duplicate dupe, duplicate the dupe, and duplicate the dupe. If candidate is same as prevnum, then do not consider this case, as it is unnecessary repeated work. There we go. So yeah, glad I figured that out. But yeah, but then that way it's like, you know, I have a 1. And then it's like, oh, my prevnum is equal to a 1, right? And it's like, I'm about to add a 1 again. And it's like, okay, how about we just add the case where we have 1, 1, right? That way we have both this 1 and then this 1, 1, right? And then it's like, okay, from here it's like, you know, only add this case over here with 1, 1, and 1, right? And then that way when you finally get to, you know, 1, 1, 1, and then a 2, and it's like, okay, we can do this case, we can do the other one, blah, 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 blah. Actually, since this is combinations, can we do sorted candidates, right? And then once we have the sorted candidates, can we do this? Wait, okay. Yeah, that works. We're 43. We're getting close. Can I do maybe set of res, and then this is an array? Dot append top of res. All right, maybe this is a little faster. Maybe not. Maybe not. Ooh, although I learned from another video that for some reason collections.deck is beefed AF. So let's do that maybe. I don't need a memo, right? Let's try submit this. Yeah, so we're still at 40, but yeah, we're inching our way closer and closer and closer here. So we have a current sum, a res, a previous num. We do if it's greater or equal to this. Our candidates, we will do and then return. Right, maybe that makes things a little bit faster. Let's submit. Then here we'll do new sum equals first sum plus if new sum set of targets. Yeah, only do that if we need to. Right, maybe that makes us go a little faster. We're just gonna keep inching our way there. Yeah, there we go. And now we're in the standard deviation curve. Nice, 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 nice. Okay. I don't know if I'm gonna be able to optimize much more, right? It's starting to get a little too complex here for my liking. Okay, otherwise it's not a bad solution. All right? Here we'll do a prev num. And here we'll do num. And this is an int or num. Right, so submit one last time. There we go, 27 ms, bada bing, bada boom, right in the standard deviation pack, which is exactly what we like to see. So there we go. So as always, in other videos, I do a quick recap of how I was able to solve the problem. So this one was rather straightforward, just a little bit tricky with the TLE tactics there. But essentially it's just combination 1, except it's a little easier in the sense that now you can only use a candidate once, so you don't even have to recurse on the same index and so on, so that makes your life convenient. It'll essentially be the same problem as combination 1, except that when you choose an element, you still go to I+1 no matter what, instead of just keeping yourself at I, and there you go, so you can sum it as many times as you want. And now, a little bit of a trickier part is it says that the solution set must not contain duplicate combinations. And so one way, obviously, is to, like, sort candidates the way that I did. And then that way, whenever you append something to res, you append the tuple of that value. And then you convert everything inside of res as a set. So essentially, delete all duplicates and then convert it back to a list, so that way you have the non-duplicates version of the things, right? But this actually does something else, because one thing I realized with this problem is that if you have a bunch of ones like this, this is actually going to kill you, right? Because essentially, I kind of drew this earlier, but if you do regular backtracking, you consider the case 1, and then from that you'll consider the case 1, 1 as well as 1, and then here you'll consider, like, 1, 1, 1 as well as like 2 1 1s and a single 1 and so on, and you will essentially have like a ton of these 1 1 1 1 1 1 1 1 1 1 1s, like an exponentially larger these 1 1 1 1 1 1 1s, because every single time you're going to say, oh, yes, included or not included, right? And essentially, you can have up to, how many ones can you have? Up to 100, right? 2 to the 100 is not a very pretty number, right? 2 to the 100 is essentially equal to 4 to the what? 4 to the 50, right? Because this is 2 to the 100. So 2 to the 100, yeah, 4 to the 50, which is equal to, if I square this guy again, 16 to the power 24. Yeah, this starts becoming a very nasty, nasty, nasty number, right? We know that 2 to the 32 is 4 billion, 2 to the 64, unsigned bit, like it's going to be double that all the way up to 100. We know that this is a crazily huge number, right? So when you have a bunch of ones, you're essentially going to get murdered, right? In terms of time complexity, if you do regular backtracking. So one way you can do it is essentially, it's like, hey, take these results that you see, like, essentially this is the same code as combination sum 1, except for there's, minor details where it's like, okay, now it's like you can't include the same numbers, so you do I+1 instead of I, and like, do this little set list trick, so that way you get rid of duplicates, and that's kind of similar to the last video. So the really, really meaty part that I kind of need to explain for this problem is essentially, this like, hard part over here of like getting around these ones, right? And in fact, I actually did this problem as one of my daily NeetCode challenges, and when I did it, I did not know how to go around this. We had to call up my beautiful friend Noor and ask him, like, yo boss, how did you do this? And he told us how he did it, and we were like, oh my gosh, that's so impressive. Because I actually did this problem as a peer programming one with my friend Gabriel, and in case you're curious about that video, I'm pretty sure I did it with Gabriel. Because I'm pretty sure this was the problem that we struggled on. It might have been another one, so maybe I'm wrong, but I'm pretty sure it's this one. So in case you're curious, I'll leave a description. I'll leave a link down to that video down in the description below. But where I actually struggled on this problem when I was a little bit more of a LeetCode noob. And yeah, but essentially the way that you got around this is one way you can essentially say, like, hey, you take this res, this is my current result. You can always turn this into a tuple, and you use, a self.memo to essentially remember solutions that you've already gone through, right? And so here's like, backtracking case 1, backtracking case 2. Here I can do, like add into my memo the tuple of res. And that way it's like at the very beginning of each backtrack, I say, hey, is that tuple of res already in my memo? And if it is, that means it's like, okay, I've already explored the solution. I don't need to explore it anymore. And that's one way to get around this thing, right? Otherwise, the other way to get around this thing, the way that I did, is essentially realize, like, hey, if the current number you're about to add is the same as the previous number, you really only need to go down one of the backtracking chain tracks, right? Because let's say it's like, let's say you have an array with a bunch of elements, A, B, all the way up to Z, and then you have a 1 here, right? And here you're about to add another 1. Well, if you're about to add... Oh, sorry, my My computer is being a little funny. If you're about to add another one, let's think about this, right? You're going to do two cases. You're going to do the cases where you don't add the 1, and you're going to do the cases where you do add a 1, right? So what about just doing the case where you add the 1, right? Because that way, essentially, otherwise, this guy will start exploring itself, right? And if this guy starts exploring itself, it'll add this 1, 1 in the same way and so on. And that's very annoying, and you'll just keep going. And like essentially, one of this guy's explorations will essentially be the same as this guy's explorations, right? And so it'll be like, you know, recursive hell until you reach the very end. So if you reach a case like this, let's ignore the case where we don't add any numbers, right? Because that way, we can essentially already cover the case where we add that same number 1 in the case where we only append that number, and otherwise, you know, any other number that is, you know, not the same and whatever, we can essentially, because wait, we can actually do better than this. This is not just previous number. We can do used numbers, can't we? I'm realizing this is going to be stronger, right? Here, we can do used and make this a set. Wait, I'm either a genius or I'm tripping here. Set. Candidate. Right? Here we'll do used. Here we'll do assert candidate not in used, use.add candidate, here use.remove candidate. Will something like this work? Or am I tripping here? Oh god, maybe I need a frequency dict. Yeah. Maybe I make this a dict. Default dict of int. Plus record 1. Used of candidate minus record 1. Right? Sorry about that. I have another video that I was currently recording at the same time that just accidentally popped up. But yeah, let's just keep going. Use candidate plus record 1 minus record 1. If candidate not in used, use.add. Self.backtrack. Used. Yeah, so we don't want to do this anymore. We want to do, as long as it's not there, right? If use of candidates. So here we'll do used of candidates is greater or equal to 0. Is equal to 0. Then we can do used of candidate plus record 1. Used of candidate minus record 1. What about something like this? No, not quite. 116, 17, 125, we're missing 26. Interesting. Yeah, because we're not using that candidate in here. Okay, but this actually doesn't make us that much faster. Really? Really? Maybe we can remove this assert. Dang, that doesn't make us faster? Yeah, use candidate. Yeah, obviously this is the case where we don't add it, so obviously don't add it there. Yeah, obviously we need it in here, right? If we start removing this, then it's completely pointless. Yeah, we TLE because of that one annoying guy. Dang, so we're actually not faster with that. That's crazy. It should make us way faster. I guess the prev num 1 is just fast because it handles the 11111 cases faster. But this one technically should be the Holy Bible. Maybe this makes things a little faster. Wait. Right. Just dang. Really? That does not make it faster. Sorry. By the way, I know this is the solution explanation and so on. But yeah, one thing I'm realizing is like, as I'm explaining this, I'm like, wait, this is going to work for any previous number because you're doing a subset and so on. So it's like, you don't want to include, well, if you've already done like, you know, a certain permutation of numbers before, you only want to do it again, like, you want to make sure that this one is the one that introduces new numbers, right? Otherwise, it'll be handled by the case above, so that when you branch and so on, it'll be kind of clever, right? It's essentially the prev num idea that I was kind of explaining. It's just, it'll work with essentially like, you know, any previous num that you're adding in there. So yeah, it's just the only thing I'm realizing is like, why doesn't it not make my solution, you know, giga fast? I guess the reason why is because it's like, you know, this is technically better. It's just that like, the one they screw you really on is the 11111 case, right? And so really, if you just do the prev num tactics, then it's like, it's like this is the one you really need to optimize for, right? So I don't know what others are doing, but honestly, I'm kind of proud of this solution. This is quite clever. It's actually it's kind of hard to wrap your head around, but yeah, the point is, if you have something like this, right? And here it's like, you know, you're about to introduce the number b again, right? Here it's like this is b. You'll introduce b as well as b and b, right? What I'm saying is, so this is kind of the problem, right? If you do a, b up to z, and then you reintroduce b, right? Well, you're going to get the exact same case out of it, right? As well as the one where you add b. But if you chose to go alongside this path, right? Here, wait, let me think about this to make sure that I'm not explaining things in an incorrect way, because now I'm confusing myself here, just because I kind of changed my solution midway through the explanation, where now it's just not just the previous number. Because here, if I'm going to go and choose to add the number, then yeah, okay, I'm essentially going to always have the current cases, right? Because what about when I don't want to add the b and I want to see an f later on? Oh yeah, because this one will pop and do the remaining case. Yes. Okay. Yeah. So basically, this is all in short, to just remove repeated work, right? So like the easy example is something with like the 111. If you just do like, you know, 1, and this becomes, you know, 1 as well as like, you know, 1 with naive backtracking, and this becomes, you know, 1 with 1 comma 1 with the 1 comma 1 with the 1 comma 1 comma 1. You can already notice there's going to be repeated work, right? Versus if you do, you know, this one, and you choose to only add the number, so like here, like 1 comma 1. and here you choose to only add a number like 1, 1, 1, right? Here, like, you'll go on from the rest of the problem, right? But when you come back to this guy, you will pop the element from the list and then do the rest of the things that you would have done, you know, from that position 1, 1, as if you had done the brute force backtracking from that point on, right? The point is that, like, here, we'll come back to here, we'll do this, and then we'll pop. And then when we pop again and so on, only then will we come in here and actually consider that solution, right? So that's essentially, okay, that makes a lot more sense, gee golly. The point is that, like, you essentially reduce unnecessary repeated work, right? Where it's like, here it's like, okay, you'll have to explore this guy, this guy, this guy, this guy, and from this guy, so from this guy and this guy, it's easy to tell that this will be duplicate work. Also from this guy, when you pop the last one, it'll come on and do this guy and so on. So it's just like, you have like triple repeated work for absolutely no reason. So you might as well only do a chain, where it's like, if you've already used a number before, then only do the case where you add the number, because you'll implicitly have the other case get covered inside your own case when you go back to pop and do the rest of the problem from that point on, right? Because essentially you'll get back to when you don't have any duplicates and essentially add the numbers from then on, and, like, you know, this case is the one that will have the duplicates. The point is that you won't exactly come back to this case, you'll come back to the case all the way to the beginning, skip those numbers, so come back to the beginning, skip those numbers, and get to the point where you only all the missing cases that you had before. Honestly, like, this is really hard to explain. How can I do a better job of explaining this? If you, the point is, like, if you have duplicate numbers, right? What I'm claiming is you should only add instead of, like, you know, doing the case where you don't add. Because when you add, essentially you keep on going and you add a bunch of duplicate numbers, and then with all your duplicate numbers, you'll essentially have the remaining rest, right? And you don't even want duplicate combinations, right? And remember, all you want is combinations that result to the same target. So then when you backtrack, right, you keep popping, you keep popping, you keep popping, you will never do the other case where it's like you explore from that point on, which you don't want to do because you essentially have duplicates of the same number, right? And so you don't want to do all those cases. So you'll come back all the way to the point where you don't have duplicates, and then go on from there and so on, which will essentially have all your remaining cases, because by definition of having the duplicates and so on, different, you know, combinations of the duplicates will essentially be the same numbers anyway, and they'll return the same sum, but more importantly, there'll be duplicate solutions in terms of the numbers that are in there, and in the solution you don't want duplicate solutions in the first place, so it's like a convenient side effect to be able to essentially get around that criteria. So I mean, like, I really hope that makes sense, because it is pretty tough to explain. It's just as tough to honestly understand. Like, this is, like, you know, it's kind of a mind-boggling problem to kind of get your head around. I'm honestly generally convinced. I don't know if I would have noticed this unless I remember the call from Nor when I did this problem. It just was so memorable, because, like, I'll literally leave a link down to the description below to when I did that problem. I literally had like a eureka moment, like, Nor, you're such a genius, and it was right next to Gabriel. So of course I remember that daily code. So that's why I remember that guy. But yeah, but I mean, I still would have solved the problem, just because it's like, you know, I would have, like, you know, converted res into a tuple and be like, okay, that's good enough. And what that does is essentially, it's like, okay, if I've already seen a combination of ones, don't start doing that again, right? Skip. And so it's essentially the very same concept, right? It's just that here, this is doing it in a bit of a cleaner way. It's just, I'm kind of shocked that it's still not a very efficient solution. But I guess I'm kind of like in this standard deviation area around here. And with what I did before is like only do previous num. And that actually, okay, there we go. So we're at 33% now. And I think the reason why previous num, even though it's a worse solution, I think it's faster, because the solution that really screws you is when you have a bunch of ones. So you might as well just be checking for ones. So if anything, you could just do, like, you know, num ones, right? So it's like, you know, you could probably, like, yeah, you can do a technically worse solution by just doing, like, you know, num ones. So here we'll do 0. Here we'll do num ones dict. Here we'll do an int, and here we'll say num ones plus or equal to candidate is equal to a 1. Here we'll do num ones minus or equal to candidate is equal to a 1. And here is like, you will do if num ones is equal to 0. Then do this, right? Let me just make sure that, oh yeah, here we'll do self.backtrack of I plus 1 with cursum res num ones, right? And then here it's like, okay, let's grab this guy, let's comment this out. Here we'll do num ones, right? So it's like, okay, used, 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 used. So let's run something like this. Okay, I gotta be careful here. Wait. Num1s plus or equal to whether candidate is equal to 1 minus or equal to whether the candidate is equal to 1. But otherwise I can do the prev num tactic, right? Should I do less than or equal to 1? Oh, no. Wait, what? Maybe I just do. What? Okay, I mean, otherwise I just do it based at the prev num. I'm confusing myself here. Oh my gosh. Or I guess it's just, yeah, just. Oh yeah, because I only want to do of course. This is only going to be, because again, I only backtrack to the point where it's like I remove duplicates and so on. So it's like I only want to do this. I don't want to do this in general based on the terms of number of ones. I want to do this based in terms of when I have a bunch of duplicated ones together. So that's why this is not going to work. Okay, yeah. Again, like this problem is quite tricky. You have to be careful. Like you really have to understand this in your head. Just to not get killed by these tiny little edge cases over here. Yeah, this completely makes sense. So the way you get around this is actually just like before, right? You just check if the previous number is a 1. That way it's like, you for sure you're in a group of 1s, right? So, but again, and that turned out to give us like, faster solution. So yeah, this all makes sense to me, which I'm glad. But yeah, this is pretty tough to explain, I'm not gonna lie. I mean, if this solution makes sense, then great, like awesome, I did my job. But I understand if I didn't, because yeah, this is kind of tough to explain, and I'm realizing like going in circles, maybe this is not the best explanation in the world. But yeah. So yeah, now we're back at a good case. So yeah, we submit this guy again. So yeah, the prev num trick makes sense if I do it again. So yeah, now it's what? Wait, why is it 5%? What the heck? Why is it 5%? I don't get it. We were here, no? Okay, I mean, all right. All right, now it's just giving me 5% for no reason. Like, all right then. Yeah, I mean, okay. A lot of stuff to go through, but yeah, so hopefully, like, big takeaway from this problem is if you essentially have a bunch of duplicates in a row, right? You want to make sure that you don't start reconsidering the same, like, combinations of those duplicates, right? You'll, like, if you, like, okay, that's probably the best way I'm going to be able to explain this. If you have a bunch of the same duplicates in a row, right? Here's, like, you have, x, y, comma, dot, 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 comma, z, and here's, like, here we'll do dot, 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 comma, a, dot, comma, b, c, d. da da da, comma A, da da da, comma A, BCD da da da. So yeah, if you're case where you have a bunch. Okay, sorry about that. If you're ever at a case where you have a bunch of duplicates like this, essentially the way to think about this is you're going to want to do the case where you only include one of those duplicates once, one of those duplicates twice, one of those duplicates 3 times, one of those duplicates 4 times, one of those duplicates 5 times, right? You don't want to do like, the case where you include 2 duplicates twice, right? Or more times and so on. Okay, this is actually the best way to explain this. So the way you do that, essentially you say, okay, let's do the case where we only consider A, consider the one where we consider 2 A's, 3 A's, 4 A's, 5 A's, 6 A's, and etc. etc. So yeah, actually, used is probably a little bit overkill. So let's just do what we had before. Prev num is equal to an int or none, right? Just for the sake of understanding, right? Here we'll make it none at the very beginning. Here we'll get rid of this. We'll get rid of this. The previous num will be the candidate itself in case we're adding candidate. Otherwise, if we're adding nothing, we'll do prev num. And here we'll say, as long as it is not the case that prev num, as long as it's not equal to candidate, right? Then we do this. And this should make a lot more sense. Right, there we go. So again, it's only if you have one of these cases, right? So I'll delete this, and here we can resubmit. Right, and there we go, 53%. That's exactly what we want to see. So yeah, this will make a lot more cohesive sense. So again, whenever you're about to deal with a bunch of duplicates in a row, you want to be careful, right? You don't want to do like, all the single permutations, right? Because really, you're just going to want to do the combination where you just have one of those duplicates, and then 2 of those duplicates, 3 of those duplicates, of these A's, and so on and so on and so on, until you reach this B, right? You only want to do really one of each, right? You don't want to do all the possible, n factorial, however many, or like n squared. So it's like, you can do, there's n combinations of 1A's, there's, n minus 1 combinations of 2A's, and so it's like n plus n minus 1 plus n minus 2 and so on. So you're doing a quadratic amount of checks instead of a linear amount of checks whenever you have duplicates, right? And so you essentially want to get rid of that work completely, especially when you're dealing with a bunch of duplicated ones, because ones really hurt your chances, because essentially it's like, it'll take candidates many ones and so on to essentially get to, or target many ones to essentially get to target. So, every single time, you do the choose the option, don't choose the option, so it'll be 2 to the power of that number, which is just way too much, right? So that's kind of the problem there. And so again, the idea is like when you have a bunch of duplicates in a row, so it's like, okay, only do the case where it's like 1 of those duplicates, 2 of those duplicates, 3 of those duplicates. So it's like, okay, if the previous num is equal to the current candidate that we're about to add, let's ignore it, right? Let's only start adding the duplicate inside of this case, and like only consider the case where it's like we don't consider num whenever we reach a non-duplicate value, right? So that way it's like when we get to this A, essentially we'll say, okay, we have this case. Then we're going to do the case where we have 2 A's, 3 A's, 4 A's, 5 A's, 6 A's, 7 A's, 8 A's, until we get to this B, right? And once we get to the B, we'll have backtrack take care of the rest, right? Then we'll come down to this A over here. And then from this point, it's like, okay, we've backtracked through the rest. Let's pop, right? And then from whatever A is over here, it'll consider the rest, right? And then it's like, let's pop. And then it'll consider the A from here and so on and da. So you'll technically reach all the cases where with those combinations of the A's and so on, you'll just do so in an efficient manner, right? You don't have to backtrack if it is not the case that, the previous number is equal to a candidate, right? And so that's essentially the point that I am trying to make. It's really when for those cases where you have a bunch of duplicates in a row, especially in those ones where they just give you a crap load of ones together. So hopefully now the solution makes a lot more sense. I was having a lot of trouble trying to explain that, but that's essentially the point. The use set, it actually might be incorrect code that just happens to be conveniently correct in terms of the test cases they gave us, right? But the previous num one should definitely make sense. You essentially, really optimize in those cases where you have a bunch of duplicate numbers altogether, which is especially helpful in those cases where you have a bunch of ones altogether, which really hurts your time. So, yeah, hopefully this time that solution made sense. But otherwise, that's very much it for this video. If you did find it useful or enjoyable in any way, shape, or form, I would highly appreciate if you left a like or a comment. But otherwise, I'll catch you next one. So until then, ciao, my friend. Bye-bye.